Hello everyone. So this is a question from NEET 2025. Match list 1 with list 2. So in list 1 we have certain processes like Haber's process, Wacker's oxidation, catalyst like Wilkinson catalyst, Ziegler catalyst, and in list 2 we have the name of the catalyst, iron catalyst, PdCl2, this guy, and TiCl4 with AlCH3 thrice. Okay. So the chapters involved is surface chemistry, aldehydes, ketones, and carboxylic acids. So we'll go and talk about them one by one. First, we have Haber process. So it's a very, very famous and well-known process. It involves the manufacture of ammonia from nitrogen and hydrogen by using iron as catalyst. Okay, that is, we take nitrogen plus 3 moles of hydrogen gas in the presence of iron as a catalyst, and we get ammonia, 2 moles of ammonia, and therefore the catalyst that we use is iron in the solid state. And there's a little bit of extra information in Haber's process. Molybdenum acts as a promoter, so we use molybdenum also here. So it acts as a promoter. So it acts as a promoter for the iron catalyst. Okay, that is, it enhances the activity of the catalyst by increasing the roughness of the catalyst surface. Okay, so this promoter enhances activity of catalyst by increasing roughness of catalyst, that is, in our case it is iron surface. And when it increases the roughness of the catalyst surface, therefore the free valencies increases, which leads to more adsorption, and therefore the rate increases. Okay, so that's the role of promoter molybdenum in this particular reaction. So therefore A will be matched to 1. So A is matched to 1. Haber's process, the catalyst is iron. Next we have to talk about B, which is Wacker oxidation. So using Wacker's process, alkenes can be directly oxidized to their corresponding aldehyde and ketones. Okay, so alkenes oxidized to corresponding aldehyde and ketones by treating them with a solution of PdCl2 containing a catalytic amount of copper 2 chloride, that is CuCl2, in presence of oxygen or air. Okay, so we treat these alkynes with solution of PdCl2 containing a catalytic amount of CuCl2, which is known as copper 2 chloride, in presence of oxygen or air. Okay, so for example, let's say we take the alkene ethene or ethylene, which is CH2 double bond CH2. Whenever we react this guy with H2O and PdCl2 in the presence of CuCl2, and also air can be used, or oxygen, we, or this guy gets converted into the corresponding aldehyde having 2 carbon atom, which is CH3CHO, that is acetaldehyde. So this guy is known as acetaldehyde, and we get palladium and 2 moles of HCl as one of the byproducts. This is example 1. We can use one, we have one more example. We can use propylene also, which is CH3CH double bond CH2. So when we add that to water and PdCl2, again with a catalytic amount of CuCl2, and we can use air or oxygen. So what will happen? This guy gets converted to acetone, that is ketone with 3 carbon atoms. So we get CH3, C double bond O, CH3 plus Pd plus 2 moles of HCl. So therefore, B will be matched to 2. So B, that is in Walker's oxidation, we use PdCl2. Okay. Then we have third, that is Wilkinson catalyst. C is Wilkinson catalyst. So the coordination compound of rhodium with the formula RHCl PH3 P thrice. Okay, this guy, and in this particular, so this is the formula of Wilkinson catalyst. This is rhodium, this is chlorine. pH is, whenever benzene is present as a substituent. So this group is known as phenyl or pH. P is phosphorus. Okay, so the structure of this guy will be, so this guy will look like something like this. So the central metal atom is rhodium, which is connected to phosphorus. This bond is in the plane. This bond is in the plane. This bond is above the plane. This bond is behind the plane. And again, this is on the plane. So this is connected to phosphorus, which is connected to benzene rings, 3 benzene rings. Same thing with here. It is connected to phosphorus, and that phosphorus is connected to 3 benzene rings. Same thing is happening here. It is connected to 3 benzene rings. So this guy is known as our Wilkinson's catalyst. Okay, and it has an official name, and the name is chlorido tris triphenyl phosphine rhodium 2, or it is also known as Wilkinson's catalyst. This catalyst, that is Wilkinson's catalyst, is used for selective hydrogenation of alkenes. Okay, so it is used for selective hydrogenation, that is addition of hydrogen to alkenes. Hydrogenation means addition of hydrogen to alkenes. So the selective part means that the double bond at the end of the chain is hydrogenated, but double bond elsewhere in the chains are not affected at all. So I will write that down. This is important. Double bonds at end of the chain is hydrogenated, but double bond elsewhere in the chain are not affected. To understand this, let's see an example. For example, let's say we have this alkene, C, C, C double bond C, right? So whenever we react this alkene with hydrogen in the presence of Wilkinson's catalyst, so what's going to happen, as I have mentioned, double bond at the end of the chain is hydrogenated. So this part, this double bond will become a single bond and hydrogens will be added here. But double bond elsewhere in the chain, for example, this guy, is not affected at all. So therefore our answer will be, so 1, 2, 3, 4, 5, 6, 7. So therefore we will get C 4, 5, 6, 7. So this will be our answer. You can see a double bond got converted to a single bond, and this double bond remained as it is. So that's the application of Wilkinson's catalyst. So therefore C will be matched to 3. Yeah, Wilkinson's catalyst is 3. And next we have D, Ziegler catalyst. which is also known as Ziegler-Natta catalyst. So before that, we have to know what is the meaning of polymerization. So whenever we do polymerization, we have many small molecules called monomers. They chemically react and bond together to form long chains or 3D network known as polymers. So we will have huge numbers of small molecules. They are, not connected to each other, but after polymerization, they all get connected by chemical bonds and they form a very big macromolecule that is known as polymerization. So the application of Ziegler-Natta catalyst is whenever we do polymerization of ethylene or ethene. So that is carried out using TiCl4 and trialkyl aluminium. So in terms of reaction that will be, so we will have polymerization of ethene. So we will have huge number of ethene molecules. So therefore N CH2 double bond CH2. So these guys N represents a very large number of ethene or ethylene. So what are used? TiCl4 is used with R3Al, that is, trialkyl aluminium, where this R is a alkyl group. Alkyl groups are having one carbon atom less than alkenes. Okay, so whenever we have these guys as catalyst, so this guy undergoes polymerization to give us polythene. So we will get CH2 single bond CH2, and so we get a very big molecule which is known as a macromolecule. So this is ethene, this is polythene. So therefore D will be matched to 4. This is the application of Ziegler-Natta catalyst. So therefore D will be matched to 4. So therefore the final answer will be A1, B2, C3 and D4. Okay.